right, it says provide the name of the major structure, provide the structure and name of the major product that results when 1 pentene is treated with aqueous acid. 1, 2, 3, 4, 5. 1 pentene, all right, that's old IUPAC. We would say pent-1-ene. That means the double bond is right there. And then aqueous acid. So this is acid catalyzed hydration of a double bond. I'm gonna go 1, 2, 3, 4, 5. 2 hydrogens here, 1 hydrogen there. There's nothing that can rearrange to turn a secondary carbocation into a tertiary, so we're gonna get usual Makarnikov regio selectivity and get this alcohol. Were you making harder than you thought? Any other questions? You did them all, they all made sense? Nice. Any other questions about yesterday's discussion or from yesterday's discussion? So our new topic today is reduction of carbonyl carbon. We might say if you oxidize an alcohol, you get a carbonyl carbon with double bonded to oxygen, sp2. So the reagent we're going to use is called hydride, and you might recognize from general chemistry nomenclature and our formal charge assignments that if hydrogen has 2 electrons like that, it's obeying the rule of 2, and it has a -1 charge, and we call that hydride. Hydride reagents add a hydride ion, reducing the carbonyl group to an alkoxide ion with no additional carbon atoms. Protonation is going to give you the alcohol, and so if we reduce an aldehyde, we get a primary alcohol. If we reduce a ketone, we're going to get a secondary alcohol. So there's 2 common hydride reagents. There's actually more than just 2. Sodium borohydride based on boron, and this thing called lithium aluminum hydride. And if you go look at the periodic table over there, you see a Roman numeral 3 above aluminum. Aluminum normally forms +3 cation. And so you can imagine if you put 4 of these negatively charged things around it, it's going to have a negative charge counterbalanced by lithium there. So they don't have a simple structure like sodium hydride or lithium hydride. The bonding to the metal makes the hydrides more nucleophilic and less basic. It's kind of nice because we can run these reactions in possibly a protic solvent, where you saw with Grignard reagents and lithium organometallics, super strong base, easily protonated. So sodium borohydride, it's a nice hydride source. Carbonyl carbon gets attacked by the hydride. The electrons jump onto oxygen. We get an alkoxide ion. Then the alkoxide is protonated by dilute acid. And the sodium borohydride only reacts with aldehydes or ketones, not with esters or carboxylic acids. Notice these also have a carbonyl carbon. So sodium borohydride can reduce a ketone or an aldehyde in the presence of acid or an ester. So here's the mechanism. Carbonyl carbon, hydride comes along, slams into this. You probably see the drawings where there's a little delta plus here and a little delta minus there because oxygen's so electronegative. Hydride goes on there. So here's the alkoxide ion. So carbon went from being S2 hybridized, sp3, and then protonation with an acid gives you alcohol. So notice here we have a ketone, and here we have a secondary alcohol. So a point of nomenclature, how do you name an aldehyde when it's a substituent? Well, an aldehyde requires that you have hydrogen on carbonyl carbon, so if you just have a single thing like this, we call that carbaldehyde. So a cyclohexane-rene, we just name this cyclohexane carbaldehyde. Here's our reducing agent. Notice this is a protic solvent, but that previous slide said this hydrogen won't, or this hydride when it's hooked up, doesn't want to get protonated by the protic proton on ethanol there. So hydride slams in, those jump off, presumably protonated cyclohexymethanol. So here's a ketone, butane 2-one, sodium borohydride, and now we have butane 2-ol. Turn carbonyl carbon into an alcohol. Ketones go to secondary alcohols, aldehydes, primary alcohols. Any questions on this stuff? None. All right, lithium aluminum hydride is more powerful, and that's kind of nice. It's kind of nice to have weak things, powerful things. That gives us some regioselectivity perhaps. Stronger reducing agent than sodium borohydride. Dangerous to work with. That's half the fun. All right, reduces ketones and aldehydes into the corresponding alcohol, but it also converts esters and carboxylic acids into primary alcohols. So to compare and contrast this to the sodium borohydride, let's just go back there. Point number 4 here, sodium borohydride cannot reduce esters or carboxylic acids. However, lithium aluminum hydride will convert esters and carboxylic acids into primary alcohol. So here we see an ester methyl benzoate perhaps. So this is an acronym, lithium aluminum hydride, and it looks just like the sodium borohydride we looked at. Well, we had cyclohexene and not a benzene ring, but it would all work the same, primary alcohol. And the mechanism similar to that of the sodium borohydride. You can just imagine hydride hitting there, those electrons jump up, we have an intermediate. Whoa, I got ahead of myself. We probably have that strong leaving group business. We'll probably get the mechanism here in a second. So it's nicer that one's weaker than the other. Well, this one reduces everything. Sodium borohydride, only ketones and esters, and only ketones and aldehydes, but not esters and carboxylic acids. Lithium aluminum hydride reduces all of it. So this makes for fun, interesting problems. Here we see a ketone group. Here we see an ester group. Here's the sodium borohydride. So we look at the carbonyl carbon on the ketone and make an alcohol. This hydrogen is the hydride that hit it. And the ester part, we leave alone. Now we see a lithium aluminum hydride. We're gonna wanna make an OH there. And then here, put 2 hydrogens and an OH. 2 hydrogens and a OH. Don't really care about that until I give you a cyclic ester. So other ways to reduce carbonyl carbon is catalytic hydrogenation. You've seen it before when we reduced what to an alkane? Right, alkenes. And we'll probably look at that in more detail. I get excited about redox chemistry. All right, so those double bonds get reduced just like an alkene to an alkane. Get a alcohol there. And it says this reaction is not commonly used because if you have double or triple bonds or other pi bonds in the molecule, they're going to get reduced as well. So there's no selectivity. So if you needed to keep a double bond in a molecule, but you wanted to get rid of carbonyl carbon and turn it into an alcohol, you'd want to use one of those hydride reagents. So why do we talk about sulfur in the alcohol chapter? It's actually a law. What type of law? Everybody's so shy and bashful. Periodic law, periodicity. Sulfur's in the same column as oxygen, so it has the same electronic structure, very similar. That's why, I'm getting way excited. I just remembered the slides I put in a couple of days ago. Going to talk about something exciting here at the end. Sulfur analogs are called thiols. The SH group is called a mercapto group. Has to do with mercury and probably some Latin word. All right, named by adding the suffix thiol to the alkane name. So instead of chopping off the E and adding OL for an alcohol, we just flat out say the name of the hydrocarbon, methane thiol, instead of methanol if it was an alcohol. So here's straight up 4-carbon chain, butane. We'll call this butane 1-thiol. Sulfur's there. Oh, excitement. It's almost like a dial, right? We got the thiol group, we have the alcohol group. 2-mercapto. That must mean the alcohol has priority over the thiol group. Common names are formed like those of alcohols using the name of the alky group with the word mercaptan. Yours and mine favorite topic, acid-base chemistry. Thiols are more acidic than alcohols. Who wants to tell me why? From chapter 17 in Gen Chem. I don't have to look over the tops of my glasses anymore. I hate all those videos. I go like this every question I ask. This is larger. That charge is more delocalized. Maybe since it's spread out, the hydrogen comes off easier. It's simple electrostatic physics. All right, so how much more here? Wow, 10.5, 15, quite a bit more acidic. Remember, this is logarithmic. For comparison, ethanol, pKa of 5.9, water, pKa of 15.7. How do we synthesize a thiol? Well, I told you, SN2 reactions, alkyl halides, the building blocks, alkyl halides and substitution reactions. So here's an interesting reagent. We have a bottle of this in the lab and it says, warning, you get this, pour some acid on this, you'll make H2S. What do you know about H2S gas? It's poisonous like monoxide, the same modality in your body. Suffocates you from the inside, your blood can't hold oxygen stuck to it. To prevent a second alkylation, use a large excess of sodium hydrosulfide with the alky. Here we get to the fun topic, thiol oxidation. I think we might have covered it previously. When you increase the oxygen content on an organic molecule, we call that oxidation. If we decrease the oxygen content, we call that reduction. We can flip it around in terms of hydrogen. When we increase the hydrogen content on a molecule, we say it gets reduced. If we decrease the hydrogen concentration, we say it's oxidized. And then that makes sense if we catalytically reduce an alkene to an alkane using hydrogen, we can define it as a redox reaction. So here is 2 cysteine residues. What is cysteine? How many of you have taken biology? Didn't you take biochem? You're in it right now. Have you studied any amino acids? This is an amino acid. There's the amino part, there's the acid part, there's the side chain. There's like 26 of them. You got to memorize them all. All right, so these things are found in proteins. And notice we take 2 hydrogens away and link this up. We call this a disulfide bond. And so we call it oxidized. The hydrogen content has gone down, and we can take this the other way, and we say it's reduced. You know, look at this whole thing, kind of look at this whole thing. The hydrogen content has increased, so we can call it reduction and oxidation. Thiols can be oxidized to form disulfides. Here's the disulfide. The disulfide bond can be reduced back to the thiols with a reducing agent. The only thing I don't like about my new setup is I don't know which slide's coming up next. The Wikipedia speech right here. How many of you don't like your straight hair and you get a perm? Raise your hand if you've had a perm. Oh, my hand did not go up. But a lot of people get perms. What's the worst part about getting a perm? Friends, family, you never gave somebody a perm? When you were a kid, your mom didn't like give her sister a perm? It smells horrible. That's the worst part of a perm. All right, so what is the chemistry of getting your hair permed? So I'm glad we talked about cysteine and the disulfide bond, because what is hair? If you ate a diet of hair, you'd say you're on a high protein diet. All right, so your hair strands are proteins, and there's a lot of cysteine groups in the protein. All right, and here's this thing called thioglycolic acid. And that's part of the, you put your hair up in curls and then you take this chemical and you put it all over and it smells like cat urine. The smell of ammonia. Actually, ammonia has its smell. Cat urine's a little worse. There's other things. And so this thing here, it says, being the salt of a weak acid and weak base, ammonium thioglycolic exists in solution as an equilibrium mixture of the salt itself as well as thioglycolic acid and ammonia. So there's the acid and ammonia, there's the ammonium salt. So you put this on your hair and it's able to cleave the disulfide bonds. So your hair is like this big protein and there's disulfide bonds and they're holding it together. And you cleave the disulfide bonds with one side of a hydrogen forming a new disulfide with another. So here's a disulfide bond. Here's just a sulfide. Here's another sulfide. Here's a new disulfide bond. So how does a perm work? A solution containing thioglycol ammonium the ammonia swells the hair, rendering it permeable. Now that's like a big pun to me right at the moment, because you get a perm, but permeable, like semi-permeable membrane. It makes it so the chemicals can go inside your hair. Permeable. Permanent. Didn't know that pun was going to come up. So this thioglycolic acid in the perm solution reduces the disulfide bonds in the cortex of the hair. In a sense, the thioglycolate removes the crosslinks. Then you rinse your hair. Then you treat it with a mild solution of hydrogen peroxide, which turns you into a blonde, which you wanted anyway, and which oxidizes the cysteine back to the cysteines back to cysteine. These new chemical bonds impart the structural rigidity necessary for a successful perm. So your hair is these spirals of protein. Maybe it's straight. Figure you have straight hair, has these bonds. Twist it up in the curlers. You put that first chemical on there. It breaks all these. And then they kind of move around to the shape you got the hair in. So this group shifts, and then there's another one of these groups, and then you bring it back, and so the smelly stuff like ammonia takes it this way, the hydrogen peroxide takes it back this way. It's gonna get a big fro next week. Anybody? Nobody?